Section 3.4, the mole and molar mass. So now we're going to start quantifying mass. And we're going to start quantifying matter. So let's come back and remind ourselves about the atomic theory. Matter is comprised of tiny particles which are called atoms. And combinations of these atoms, I'll shade in the ones on the outside to indicate they're a different type of atom than the one in the middle, are called molecules. And they are very, very small, on the order of 10 to the minus 23 grams. That's a pretty small mass when you consider that a pencil has a mass of maybe 2 grams. This is 10 to the minus 23rd grams, very tiny amount. So for that reason, even in a small amount of matter, so even if you were to take a little dot from a pencil, the number of carbon atoms in that tiny little dot would probably be around 10 to the 15 or 10 to the 16, maybe perhaps even. A huge number of atoms. So we need a way to quantify them. And so one way to do that is through what is called the mole. M-O-L-E. Obviously the word is related to molecule, right? Or molecular, if you want to think of it that way. But a mole is not the same thing as a molecule. A molecule is one small particle, which is a combination of some number of atoms. That's a molecule. A mole can be defined in different ways, but one way we define it is to say that if you have 12 grams exactly of carbon 12, okay? Now carbon 12 is an isotope of carbon. Right? This is a isotope of carbon that has 6 protons because it's carbon and 6 neutrons. Obviously, it also has 6 electrons. That's a specific isotope of carbon. If you have a mass of 12 grams, we will define that as 1 mole. So 1 mole is the number of particles of carbon 12 in 12 grams of carbon 12. Okay? So if you have 12, it turns out to be a number, right? Like if you have 12 grams of carbon 12, there's some number of atoms of carbon that are in that. And it turns out that number is approximately 6.02, I'll put 4 sig fig, 6.022 times 10 to the 23rd. That's the number of carbon 12 atoms in carbon 12. 12 grams of carbon 12. Okay? So that's one way to define it. That's called Avogadro's number. The abbreviation for Avogadro's number is typically a capital N for number with a lowercase a for Avogadro. Avogadro's number. And that is 6.022 times 10 to the 23rd. And we're going to define that as a mole. So if I say I have a mole of something, what I mean is there's that many particles. Okay? And it could be anything. You can have a mole of carbon 12 atoms. You can have a mole of carbon 13 atoms. You can have a mole of electrons. You can have a mole of what are called photons. We'll talk about that in chapter 6. Doesn't matter what the type of particle is. It's just saying there's some number, Avogadro's number, we're going to define that as a mole of whatever it is, okay? So in a sense, a mole is just a way to count things. Just like we would use a dozen, right? 1 dozen is 12 particles. So if I say I have a dozen eggs, you'd say, okay, I have a dozen eggs, that means you have 12. If I have 2 dozen, that means you have 24. 1 mole is the same thing, it's just a bigger number. Now, why use such a big number? Well, because atoms are so small, molecules are so small, that even a small amount of them is a huge number. Okay? That's essentially the idea. Avogadro's number. Now, mainly what we do in this section is conversions involving that. So what I'm going to do is I'm going to move on to a topic that is related to this, and it's called the molar mass. Okay. So this is the mass of a substance when we have 1 mole of that substance. Okay, that's what that means. That's the molar mass. It's the mass of a substance if you have a mole of it. So what we would claim is that if you have 6.022 times 10 to the 23rd carbon-12 atoms, okay, that's 1 mole of carbon-12, right? We talked about that previously. But we would also actually figure out how much that weighs, and it turns out it's 12 grams. Okay. Now, it's probably not possible to have a mole of carbon-12 without any impurities, but imagine that you did, and you said, how much does it weigh? Well, by definition, we're saying it weighs 12 grams. We said that earlier, right? We define the mole that way. If you have 12 grams of carbon-12, we're going to define that as a mole, which is Avogadro's number here. Okay? So it's all sort of circular argument in a sense. But essentially, it works for us. So here's what we do. If you look at the mass of the hydrogen atom, it's approximately a 12th of a carbon-12 atom. Okay, it's not exactly a 12th, but it's pretty close. It's like within 1% of that. And if you look at the mass of a helium atom, it's approximately 1/3 of a carbon-12 atom. Approximately 1/3. So what we do is we use the periodic table to catalog these masses. Of the elements, right? You actually see that in chapter 2 when you do general chemistry. And so here's what we'll claim. If we look at the periodic table, and I'm just going to pick a few elements. So element 1 is hydrogen. This is essentially the mass in grams when you have 1 mole of hydrogen. Okay? In other words, if you have 6.022 times 10 to the 23rd hydrogen atoms, that's how much it would weigh in grams. Again, a pencil weighs around 2 or 3 grams. So if you had a mole of hydrogen, it would weigh in the order, close to that of a pencil, maybe 1/3 of a pencil or something like that. Okay? Just a few grams is how much that weighs. If you look at the second element in the periodic table, element 2 is helium, right? That would give you your mass in grams of 1 mole of helium. Isn't that cool? So we now have masses corresponding to a certain number of atoms, which is this Avogadro's number, which is the same as a mole. So we're going to call these masses, we call them molar mass. And they're available for use in the periodic table. So for example, hydrogen, 1.01. Now I'm going to give you your units, grams per mole. 1.01 grams is the mass of 1 mole of hydrogen. Just like the density of water is 1 gram per milliliter, meaning if you have a milliliter of water, the mass would be a gram. That's the density of water. The molar mass of hydrogen is 1.01 grams per mole, meaning that if you have 1 mole of hydrogen, the mass would be 1 gram. That's 1 mole of hydrogen, atomic hydrogen, not molecular hydrogen. So helium, for example, would be 4.00 grams per mole. And these numbers, these molar masses, are available in the periodic table. So another example would be oxygen, 16.00 grams per mole. Another example would be neon, which is 20.18 grams per mole. So forth and so on. Iron, if you want to look at a metal, 55.85 grams per mole. So the periodic table ends up being very useful for mass calculations because it essentially tells us how much mass we would expect a given amount of substance to have. So that's useful, right? Like if you think about it, if you're trying to load trucks onto a ship and ship that, the trucks across the ocean, across the Pacific Ocean, you might want to know how much those trucks weigh so that you know how many that ship can handle, it can hold. Okay? Size is usually the bigger issue than how much they weigh, but let's suppose that weight's an issue. So knowing the mass of a truck would be important for knowing how many you can fit in there. For chemical reactions, knowing how much mass reacts is useful as well. Okay? So that's called the molar mass, and the units are in grams per mole. But we can also do molar masses of compounds or molecules, and that's kind of cool. We don't have to limit ourselves to just the elements. So for example, let's find the molar mass of water. Well, water has a chemical formula H2O. So if you want to find the molar mass, all you got to do is look up the masses in the periodic table, the molar masses of each element, and add them up. So there's 2 hydrogens, right, in water. So 2 times 1.01. There's only 1 oxygen, so 16.00. And you get 18.02 grams per mole. So 1 mole of water has a mass of about 18 grams. Okay? How about if we were going to do something a little more complicated, like glucose? Let's find its molar mass. Well, glucose has the chemical formula C6H12O6. So that would be 6 times 12.01. Carbon has a molar mass of 12.01. Carbon 12 is exactly 12. But remember, carbon, natural occurring carbon, is a mixture of carbon 12 and carbon 13. So it's a little bit more than 12. It's 12.01. There are 12 hydrogens in glucose. And there are 6 oxygens in glucose. So that would give you a total of 180.18 grams per mole. Check that yourself. See if you get 180.18. That would be the molar mass, 1 mole of glucose. Meaning that if I'm going to draw a glucose molecule as just like a little hexagon, because the 6 carbon atoms, 5 of the carbon atoms and 1 of the oxygen atoms forms a ring, and it looks a little bit, we could draw it like a hexagon. It doesn't really look like a hexagon, but. So I just drew 6 molecules, right? That's 6 molecules of glucose. But I would have to draw a lot more to get a mole. If I was going to draw a mole, I would have to draw a total of how many? How many of these molecules would I have to draw to get a mole? 6.022 times 10 to the 23rd. Right? That's how many of those molecules I would have to keep drawing. How long would that take me? It would take me longer than I'm going to live. By a long shot, right? Perhaps we would finish 50 or 60 generations after I'm dead. Or if we had, actually you can do these calculations. Some textbooks will have problems, like if you have every human being on the earth dedicating their lives to counting molecules to get up to Avogadro's number. How long does that take? Oops, sorry, 23rd. Well, it ends up taking a billion years or something like that. It's a ridiculously large number. But that's just the nature of matter. Atoms are very small and there's large numbers of them. So that's how much it would weigh. Which, by the way, isn't that much. I mean, that's like, 100, that's like 100 milliliters of water, something like that, right? I'm sorry, 18 times 10. That's 10 milliliters of water. That's not very much water. Only about 10 milliliters, a tiny amount, okay? So that's the molar mass. Now, the main thing that you want to get out of this, don't get hung up too much on that, is that you want to be able to do particular types of calculations, which you practice in the sample problems and in the practice problems. But essentially what you do is you go through a certain set of calculations. So for example, if I have 10 grams of water and you want to find out how many moles of water that is, what you would do is you'd say 10 grams of water, 1 mole of water is 18.02 grams of water. And then the grams of water cancel and you get moles of water. So if you take 10 over 18.02, you get 0.555. Oops. Moles of water. And then if you wanted to find out the number of molecules, so if I have the moles of water, which I just calculated, and I want to find the number of molecules of water, what you do is you multiply by Avogadro's number. Avogadro's number is the conversion between moles and molecules, or moles and atoms. So 0.555 moles of water, you multiply it by Avogadro's number. Avogadro's number is really unitless. It's just a number, like a dozen is unitless. So if you take the number of moles and multiply that by Avogadro's number, so we got to put this up here, so times 6.022 times 10 EE to the 23rd. Whoops. 0.555 times 6.022 times 10 to the 23rd. Oh wow, that's not working very well. Let me put in the Avogadro's number. Oh, okay, so that's times 10 to the x function sometimes doesn't work on this calculator for some reason. So let me try it a different way. 0.555 times 6.022 times 10, oh, that didn't work either, sorry. This calculator is a bit problematic sometimes, and I've noticed that with it before. That sometimes it just doesn't do the EE very well. So I've cleared everything out, so let me try it again. 6.022 times 10 to the 23rd. See that? It's, for some reason it's not working on that. Nope. Okay. So let's cheat. 0.555 times 6.022. I won't even do the times 10 to the 23rd. 3.34. Times 10 to the 23rd. See, I don't need that calculator to mess me up on that. 0.555 times 6.022 is 3.34. And then we just multiply it by 10 to the 23rd. Okay? So if you have 10 grams of water, this is how many molecules of water you have. Okay? So just to kind of sum up that calculation, if you have the mass of a substance, what you can do is, if you want to get the moles of the substance, you divide by the molar mass. Okay, dividing by the molar mass gives you the number of moles. Actually, let me make that a little bit bigger. It's kind of hard to read that, especially on these videos. So if I want to go from mass to moles, you divide by the molar mass. Now let me ask you a question, just sort of thinking about mathematics. If you have the mass and you want to get to the number of moles, you divide by the molar mass. Suppose you had the number of moles and you wanted to find out the mass, what would you do? Well, you would just do the reverse, right? So if you have the number of moles and you want to find the mass, you just multiply by the molar mass. Isn't that interesting? So you just do the reverse. So multiplying by the molar mass will give you the mass, in grams, typically. And dividing by the molar mass will give you the moles. Okay? Now, the second calculation that we should be able to do, which I showed you an example of, is what happens if you have the number of moles and you want to get the number of molecules? Well, what we did was we multiplied by Avogadro's number, 6.022 times 10 to the 23rd. So if you want to do the reverse of that, if you want to go from molecules to moles, you divide by Avogadro's number. So think about what we did here. We had the mass, 10 grams of water. We divided by the molar mass to get the number of moles. And then we multiplied by Avogadro's number to get the number of molecules. Our calculator couldn't do it, but we're smarter than a calculator, so we were able to do it without it. If we wanted to go backwards, if we wanted to find the mass of water and we had this many molecules, what we would do is we would divide by Avogadro's number, right? You take the number of molecules, divide by Avogadro's number to get the moles. And then if you had the moles, you would multiply by the molar mass to get the mass. Do the reverse of what we did in that particular example. So those, even though I just sort of briefly showed you an example, when you do the sample problems, you'll see there's a few of these. And that's something you really want to be able to do by the time you're done with this chapter very well, is to be able to calculate the molar mass of a substance using the periodic table, and then to be able to do these interconversions between mass, moles, and number of molecules. Okay? That's essentially the idea. Now there's one kind of tossed in little topic in this section. It's really a small topic, and they give you a sample problem to work on it, sample problem 3.8. But it's this issue of the empirical formula. And the empirical formula is something that you want to look into. It's discussed in more detail in section 3.5, combustion analysis, but we also want to cover it a little bit here. So my point is this for the empirical formula, that we have this idea of what a chemical formula is. And there are different ways of representing substances. So for example, I could just give the name of something. I might call it glucose. There's some substance called glucose, and we know what it is. It's some sort of sugar. Or I could write the chemical formula. And the chemical formula is essentially a representation of how many atoms of the three elements that comprise glucose, how many atoms of each of those elements that you would find if you had the smallest possible unit of glucose. So glucose is a crystal usually, or it's dissolved in water. But if you have the smallest unit of glucose, you would find that that smallest unit has 6 carbons, 12 hydrogens, and 6 oxygens. And we call that the molecular formula. It's the idea that this, in its essence, is what glucose is. If you distill it down to its simplest building block, glucose is a combination of 6 carbon atoms, 12 hydrogen atoms, and 6 oxygen atoms. Okay? Now, we could represent that in different ways. Here's one way to represent it. We could represent it with a picture or a diagram which shows the bonding that takes place in this glucose molecule. And we would find that one of the carbon atoms is bonded to an oxygen and another carbon, and then a CH2OH, and then an H. And that the other carbon atoms are all bonded to an OH and an H. Now, I'm not showing the three-dimensional chemistry here, the stereochemistry we call it. It's too complicated for this discussion, and it's not simple. But essentially, this would be another way of representing glucose. It shows the bonding, the arrangement of atoms that are in this molecule. But the molecular formula is the main point here. This is called the molecular formula. One molecule of this substance has that formula. But if we distill this molecular formula even more simply, mathematically, okay, so if we have the molecular formula, which is C6H12O6, we'll note that there is a ratio of 6 carbons to 12 hydrogens to 6 oxygens. Okay? That is not the simplest possible ratio that represents this molecule. The simplest possible ratio would be if we divided each of those numbers by 6, right? We would get 1, 2, 1. Meaning that the ratio of carbon to hydrogen to oxygen is 1 to 2 to 1. Now, in chemical formulas, we generally do not write the subscript 1, so we would just write CH2O. And this is what we call the empirical formula for glucose. The empirical formula shows you the smallest possible ratio that accurately depicts the ratio of each element in the compound, right? The smallest possible ratio that represents 6 to 12 to 6 is 1 to 2 to 1, okay? And we call that empirical formula. Now, you might ask, what's the point of an empirical formula? But it turns out there are chemical methods, analytical methods, which allow us to determine the empirical formula, but not the molecular formula. And so the empirical formula is a stepping stone toward finding the molecular formula of a substance. Okay? So that's a discussion of that. Section 3.4, the mole and the molar mass. So make sure that as you do these sample problems, you keep in mind that the primary goal of this section, aside from understanding where these numbers come from, is to be able to do the mass to mole to number of molecules conversions.